Okay, so I think I kind of understand. This tensor Gij is symmetric. Here you can see the definition. So Ij, you can swap Ij. Is it clear? Excuse me. So Ji, if you consider Ji, this is just you change the order of this. Yeah, this xi j partial x k partial xi I. You change this order, but the same value. So this is symmetric. So that's the trick. Okay. So now we can move next one. So we have down here, then here, we have down here. So here, yeah, using a permutation symbol, as Gi is a vector in the three-dimensional space, we can express it as a linear combination of the base vectors Gi downstairs. So we have done this, where we find the coefficient Gij by using this here. Here last time we got Gjk, yeah? But this is the same as Gkj, as I just explained now. So this is okay. Thus the matrix Gij is the inverse of the matrix Gij downstairs. That is so this is more like I think it's very strange to write Gi dotted Gj equal Gik Gkj, and this is equal Ik. I would say Ik Gkj. See Ij Kronecker. So this order doesn't matter. So up, up, down, 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 up, up. But these both are Kronecker. Inverting the system, equation 3.22, inverting the system. How do you call this inverting the system? So I would say Gi, which is this, Gij, Gj, which is Gij, G, jk, yeah, ij, jk, gk. Is this correct? No. I'm sorry. Inverting. So inverting. So this is wrong. We do G. How do you call it? I think this is more like this. You multiply G Ki here. See, so this is G Ki. Yeah, and this part is chronicle Kj. Then K go through 1, 2, 3. So K will hit. No. J here, summation convention is here. This is summation convention, J. So J go to 1, 2, 3. So eventually it will hit. So this is like G, K, right? So this is it. So you obtain the GK equal G, Ki, G, I. This is vector. Yeah, so I mean this thing is the same as this thing. The array Gij is called contravariant or reciprocal metric tensor, and Gi are also called contravariant or reciprocal base vectors. We later verify that what we call tensor indeed follow the transformation law for tensors. We later verify that what we call tensors indeed follow the transformation law for tensors. From the Cartesian permutation symbol, we construct the permutation tensors. Well, now we changed epsilon, e to epsilon ijk square root, where permutation tensors, right? Where we were I think this just included, absorbed this one, right? This G factor. You put this G factor here, so you have square root of G, and you redefine this to be epsilon ijk. That's it, I think. You just redefined epsilon ijk. Where we have written the permutation symbol as eijk to match the indices with those on the left-hand side. I don't think the explanation of this book is so good. So I don't know if he's talking about this upstairs symbol. But I think up to now we encountered on only downstairs symbol, downstairs indices like this. So I think here we all of a sudden introduced upstairs indices. And the reason we do this, strange. See, do we have here? Here we all introduced downstairs symbols, downstairs indices, but then here, this is already introduced. I think we have done down indices, then you have up indices, then you have this anti-symmetric tensor. But now he will also want to introduce this pattern. Downstairs indices multiplied by downstairs indices, which is equal to upstairs indices. So where we need upstairs indices for epsilon ijk. So I think he is talking here. He talk about upstairs indices. He is not talking about E or epsilon. E or he is not talking about E or epsilon, but he's talking about upstairs indices. Permutation symbols as this, you can say as permutation symbols as this or epsilon ijk to match the indices with those on the left-hand side. Left-hand side. I think it's the right-hand side. This is right. So because here. Okay. This is left-hand side because he's talking about this one. He's talking about this one. he introduced this permutation symbol so that this is ijk up, so and ij down, right? So ij up up down down, so the remaining is k up. So the left hand side you have k up. So in this way epsilon ijk was introduced. 3.1 Vectors and tensors. As we have two systems of base vectors, gi down and gi up, any vector v can be written as v equal vi downstairs gi upstairs, or vj upstairs gj downstairs. Any vector v can be, where vi are called the covariant components and vj upstairs are called contravariant component. The raising and lowering of the indices, that is the convention of covariant or to contravariant or vice versa, can be performed by scalar multiplication of equation 3.28 by gk or by gk upstairs. Very strange. Is this scalar multiplication? Anyway, okay. He called this scalar multiplication. So the left part, this is Kronecker, and this is tensor. Yeah. And Kronecker, you have summation convention, II. So I goes to K. Very strange. I think I would say this goes to K. Because you have II. This goes to K, right? Strange. I would say this is K. VK. JJ. So this one, JK equals GKJ. This is symmetric. So then this is like, this guy should be like a GKJ. VJ. So strange. Or it's inverse. You can also consider inverse. VK. This is VK upstairs equal GKJ upstairs, then VJ downstairs. VJ downstairs. Okay. For second rank tensor A, we can have multiple representations. Second rank tensors A, we can have multiple representations. A equal A ij gij or A ij gi up tensor product gj down. A ij I up j down g I down multiplied by g j up, which is equal A ij upstairs gi multiplied by gj downstairs. Okay, we may relate the covariant, contravariant, and mixed component by using the matrix tensor and its reciprocal in the form Aij so this one you can put down. Yeah, you can put this K down, L down. So you have Ij down. If you have Ij up and KL down, you can put this KL indices to up Ij. And if you have indices like I down, J up, and K up, L down, so you lower the K indices down by this, and you put L indices up by this. Yes. Okay. I don't know why this was disconnected. If Aij is symmetric in A and in I and J, we can see that Aij up down, Aj down up equal Aij. Horizontal position. Okay, horizontal position is this. Once we have learned the basic operation using the matrix tensor and its reciprocal, we are ready to define covariant, contravariant, and mixed arrays properly. For this, we introduce two curvilinear systems, xi and xi bar, x bar I. The system xi being curvilinear is a temporary notation. We can make it Cartesian again afterward. If an array Vi in the xi system transforms into V bar I according to the rule V bar I equal Vj partial xj partial x bar I, we call it a covariant array and use a subscript to write. It's complicated. I'm wondering how much do we have chapter 3? A little bit. Let's see. It's a lot. It's a lot. Okay, let me have a break for a while. We can start from this page, like 333, page 32, 333. So we can do page 33, equation 333. Next time.